Welcome to the deep dive. Today we're taking a serious plunge into the engine room of the Scale network, specifically how it handles consensus. We've got some source material right here that really digs deep into its core protocol, its architecture.
That's right. And think of our mission today as, well, sort of reverse engineering the black box of a scale chain. We're going to unpack these sources and really try to understand exactly how a transaction goes from being submitted by you, the user,
Right.
all the way through getting ordered into a block, processed, stored,
Yeah.
and critically, how this whole complex dance leads to Scale's claims of provable security.
Provable security. Yeah, it sounds impressive, like they've got it all figured out. They're claiming guarantees around consistency, liveliness, but under specific conditions, right?
Specific conditions.
So we're going to trace the path, follow the data through nodes, signatures, algorithms. Okay, so where does this journey actually begin? The source material lays out a sequence starting with a transaction.
Yeah, naturally, it all kicks off with you, the user, initiating a transaction. The source calls this the submission phase. You sign it with a private key, and it gets sent off. The sources note this can hit a core node directly, or, interestingly, go through a network proxy layer.
A proxy layer, why?
Well, it's smart for handling traffic, load balancing, and also making sure your transaction doesn't just hit a node that's maybe offline or unhealthy at that moment.
Okay, got it. So the transaction is out there, it's hit a node or a proxy. What's the very next thing that node does with it? Does it just sit on it?
No, it doesn't hang on to it.
Yeah.
That node immediately moves into what the source calls the broadcast phase. It shares that transaction with all the other core nodes participating in that specific scale chain. The idea is making sure everyone sees it, and quickly.
Like a network-wide shout-out.
Pretty much, yeah. And when any node gets a transaction, whether it's the first one or got it from the broadcast, it enters the pending queue phase. This is where it gets its first checkout.
Validation time.
Right. Checks on the signature, the format, the basics. If it passes muster, it's added to a holding area, this pending queue.
The sources mention this pending queue has a fixed memory size. That sounds like it could be a potential bottleneck, right? What happens if it fills up?
Good catch. Yeah, it can fill up. And that's where prioritization comes in. The sources say if the queue is full when a new transaction arrives, some transactions have to be dropped. And following the pattern you see in Ethereum, Scale prioritizes based on gas price.
Ah, gas price.
So transactions with the smallest gas price get booted first to make room.
Right, the fee you're willing to pay. So higher fees basically buy you priority when things get congested.
Yeah.
Okay, that makes sense. So we've got these validated transactions sitting, waiting patiently in these pending queues on potentially many different nodes. This must be where block creation starts.
Absolutely. This leads us straight into the block proposal phase. Now, importantly, each Scale node independently decides, okay, time to propose a block. It grabs transactions from its own pending queue, orders them, usually putting higher gas prices first, up to the block's gas limit, and forms its own potential block proposal.
Wait, so every active node is potentially building its own version of the next block. How do they share these without flooding the network with, massive amounts of data?
Ah, that's handled pretty smartly. A node broadcasts a compressed version of its proposal, and this compression is key. It only sends the transaction hash for each transaction in its proposed block.
The hash.
Yeah.
The unique digital fingerprint.
Exactly. Think of it like that. So when a receiving node gets this list of fingerprints, it checks its own pending queue to see if it already has the full transaction data for each hash.
Okay, and what if it doesn't have one? Based on the hash, it knows it's missing something.
Precisely. The receiving node figures out which transactions are missing. It then specifically requests the full data for only those missing ones from the node that sent the proposal. Once it has the complete proposed block data and validates it, the receiving node takes a really crucial step. It signs a data availability signature for that specific proposal.
A DA signature.
And sends it back to the original proposer.
Okay, a data availability signature. What exactly does that signature signify? What's it proving?
It's pretty much what it sounds like. It's a signature confirming that this specific node has seen and actually possesses the data for that particular block proposal. The proposing node, the one that sent the proposal out, starts collecting these DA signatures, and it needs to gather them from a supermajority.
Supermajority.
Specifically, 23 of the nodes in that chain.
Ah, 2/3 again. Right, that number seems fundamental in these kinds of systems.
Yeah.
Is there a specific reason it's 23 and not, say, just over half, 51%?
Oh, absolutely. There is, and it's foundational, really, to Byzantine fault tolerance, which the source material references directly. That 23 supermajority is necessary because if, as Scale assumes, Less than 13 of nodes can be malicious.
Right, the bad actors.
Then any group of 23 must contain at least one honest node. It's a mathematical guarantee. This threshold is how systems like this can reach agreement even when some participants might be actively trying to cause problems. So in this phase, once the proposing node successfully collects DA signatures from 23 of the nodes, it bundles them together into something called a DA proof.
Okay, so the DA proof isn't just a node saying, yeah, I think this block looks okay. It's actual proof that 2/3 of the network has the data for that proposal.
Exactly. It proves possession, or at least receipt, across a wide segment of the network.
Yeah.
And that DA proof collection triggers the next step, the DA broadcast phase. Once a node has managed to assemble its DA proof, it broadcasts that proof, not the whole block again, just the proof to all the other nodes. And the sources really highlight that requiring this DA proof before moving forward solves two really big problems.
Okay, what are they?
First, it guarantees the proposal itself has been widely distributed. Honest nodes definitely have access to the data, or at least know it existed and was seen by many others. Second, because gathering that proof required 23 signatures, it mathematically guarantees that a specific proposal is unique.
Unique. How so?
Well, think about a malicious node trying to cheat. Maybe it tries to propose two different blocks for the same block height simultaneously. It simply cannot get 23 of the nodes, which includes a majority of honest nodes, remember, to sign off on both conflicting proposals. They won't sign two different things in the same slot. So the DA proof ensures uniqueness for that proposal content at that height.
Okay, wow. That makes sense. But now, this is where it gets really interesting, right? Multiple nodes might have valid proposals. Maybe several now have their DA proofs. How do they all agree on one single winning block for this slot?
Right. That's the job of the block consensus phase. Once a node has received DA proofs from 23 of its peers for various proposals floating around, it enters this consensus phase. The sources state this phase uses an asynchronous binary consensus algorithm. They specifically reference principles from the classic Byzantine Generals problem.
Ah, the Byzantine generals, where they need to agree on attack or retreat, but some generals might be traitors sending conflicting messages.
Exactly that problem. So in this context, nodes essentially vote. It's simplified here, but think of it like voting 1 if they have at least one valid proposal with a DA proof for the current block number, and voting 0 otherwise.
So this algorithm helps the honest nodes converge on an agreement, despite potential disruption from malicious ones.
Precisely. The specific algorithm used is designed to guarantee that all honest nodes will eventually agree on the same single outcome for that block slot. Either they all agree on 1, meaning yes, at least one valid DA-proven proposal was successfully put forward by an honest node somewhere,
Okay.
or they all agree on 0, meaning no valid proposal made it through with enough support. If they agree on 1, it confirms the winning proposal is what they call DA-safe. It was widely distributed and proven unique by that DA proof mechanism.
But wait, if they agree on one, does the algorithm itself pick which proposal wins if there happen to be multiple valid ones that all got DA proofs? The source seemed to say the algorithm guarantees one exists, but maybe not which one is the winner.
That's a sharp observation. You're right. The consensus algorithm primarily ensures agreement that a valid proposal exists. If multiple proposals successfully reach this stage, they all got DA proofs, they all contributed to the one vote. The selection of the ultimate winner comes down to priority. The sources state that the highest priority proposal among those consensus winners is chosen. And this priority isn't fixed. It rotates among the nodes.
Ah, so it's fair over time.
Exactly. It ensures that over the long run, each node gets a roughly similar chance of having its proposed block be the one that actually wins consensus and gets added to the chain.
Okay, so consensus achieved. The network agrees a valid block exists, and a priority scheme selects the winning proposal. What's the very next step?
That takes us logically to the block signature phase. Now that consensus has effectively identified the single winning proposal for this block number. Every node signs off on that winner. They create what's called a block signature share, basically saying, yes, I agree, this specific proposal is the winner. They broadcast these shares. And guess what? Just like with the DA proof.
Let me guess. They wait to collect 23 of these signature shares.
You got it. They wait until they collect 23 of these block signature shares from all nodes. These individual shares are then combined, cryptographically merged into a single collective block signature for that winning block.
Another 23 threshold, so this time it's cementing the agreement on the final winner.
Precisely. This collective block signature is essentially the network's final stamp of approval. It's cryptographic proof that 23 of the network participants agreed on this specific block as the legitimate winner for this slot. At this point, all honest nodes know which block won, and they have this powerful collective signature. However,
Oh, there's a however.
yeah, a small practical wrinkle. Due to network delays or maybe nodes going offline temporarily, some nodes might not actually have the full data for the winning block proposal yet, even though it had a DA proof way back earlier.
Wait, but didn't the DA proof guarantee it was widely distributed? How could they not have it?
It guaranteed that 23 of nodes received it back during the DA broadcast phase. But, networks are messy. Maybe the original proposer went offline after collecting the DA signatures, but before every single node managed to download the full block from it. Or maybe a node just experienced temporary packet loss. This brings us to the block finalization phase.
Okay, so how does a node catch up if it's missing the winning block data at this stage?
Because that DA proof did guarantee widespread distribution among that crucial 23 supermajority, a node that finds itself missing the winning proposal knows it can simply ask its peers. It connects to other nodes, confident that at least 23 of them, likely many more, will have the full winning proposal data, which can be verified using that collective block signature they all have. So it just downloads the missing block data from its peers. This is how nodes ensure they all eventually converge on having the exact same finalized block.
Got it. So catch-up is built in. The finalized block is now definitely available on the node. What's the very final step before moving on to the next block?
That's the EVM processing phase. The now finalized, fully available signature verified block is fed into the Ethereum virtual machine, the EVM. This is where the computation happens. The smart contracts are executed based on the transactions included in that block, and this updates the state of the scale chain.
And finally, the storage phase.
Correct. The committed block itself is stored. Now, the sources mention block rotation, meaning older blocks might eventually be pruned to save space, but the EVM state updates resulting from those blocks are permanent. That's the critical part. So the updated EVM state, representing the outcome of all those transactions, is saved, and then the node is ready. It resets and prepares to participate in the whole consensus dance for the very next block.
Wow, that is quite the intricate journey for just a single transaction to make it through. The source also briefly mentions a block catch-up mechanism. How does that fit into this whole picture? Is it different?
Yeah, that's described as a separate process, kind of running in parallel. It's designed for nodes that maybe join the network late or were offline for a while, or maybe they're just observer nodes that don't actively participate in the core consensus rounds. These nodes don't need to go through that whole multi-phase proposal, DA-proof consensus voting thing.
So what do?
They simply download already committed, finalized blocks from other nodes. They can easily verify these blocks are legitimate because each one carries that collective block signature we talked about, the one requiring 23 agreement. So they just pull the history and check the signatures. The source says nodes might also periodically use this mechanism just to double check if they somehow missed any blocks.
Okay, that makes sense for keeping everyone synchronized.
Yeah.
Right, we've truly mapped out the mechanics now, how blocks get built, agreed upon, finalized. Let's pivot back to that provable security claim. The source material grounds this in two key properties: consistency and liveliness. What do those mean here?
Right. So consistency in this context essentially means that eventually, for any given block number, say block 1 million, every single honest node on the network will have the exact same committed block, and crucially, the identical EVM state that resulted from processing that block. The eventually part is important. It acknowledges that network delays happen, but they'll all get there.
And liveliness.
Liveliness simply means the chain doesn't just grind to a halt. It guarantees that the network will always continue to finalize and produce new blocks. It keeps making progress.
Okay, consistency and liveliness. And the provably secure part means these two things are guaranteed. But you mentioned earlier it relies on specific conditions and mathematical assumptions.
Exactly. The sources are very clear. This isn't some kind of magic, unconditional guarantee. It's proven secure if certain assumptions about the nodes and the network hold true. There are two main categories of assumptions mentioned.
All right, let's start with node security. What's the core assumption about the nodes themselves, the participants?
The fundamental assumption is about the proportion of potentially malicious or faulty nodes. The source states that out of the total number of nodes n in a specific scale chain, at most 13 are Byzantine or malicious. They use that notation, 3t plus 1n, where t is the maximum number of malicious nodes. So if you have, say, 16 nodes in a chain, the system security proof assumes no more than 5 of them, since 35 plus 1 are malicious. If 6 were malicious, the proofs don't hold.
And what does malicious actually mean here? What kind of bad things would they try to do?
Well, a malicious node is basically one that deviates from the protocol rules. It might try to double spend by proposing conflicting blocks, like we discussed, or maybe send garbage messages. Or perhaps more subtly, it might just not send messages when it's supposed to, trying to stall or disrupt the consensus process.
Ah,
But crucially, the sources explicitly state an important limitation. These malicious nodes are assumed not to be able to control the underlying network infrastructure between the honest nodes, meaning they can't just intercept, censor, corrupt, or arbitrarily reorder messages that are being sent between nodes that are following the rules. The communication lines between honest nodes are assumed to be safe from direct tampering by the malicious nodes themselves.
okay. Assumption one. Less than a third of nodes are bad, and the bad ones can't mess with the direct communication lines between the good ones. What about the network itself? What's assumed about, the internet connection between them?
Right. The scale algorithms are designed based on the assumption that the underlying network is asynchronous and reliable, with an eventual delivery guarantee. Let's break that down.
Okay.
Asynchronous means there's no fixed upper bound on message delay. Messages might get there really fast, or they might be incredibly slow, sometimes arbitrarily slow, in theory. Reliable with eventual delivery guarantee means that even though messages can be slow, any message sent between two honest nodes is guaranteed to get through eventually. It won't be lost forever.
Arbitrarily slow, but eventually delivered. That sounds like it's trying to model the real internet, which can definitely be slow and messy sometimes.
It absolutely is. The sources explicitly connect this assumption to how the modern internet behaves. You get temporary packet loss, connectivity issues, routing delays. But usually, things resolve. In practice, since the real internet can actually drop packets permanently sometimes, this eventual delivery guarantee is typically achieved through mechanisms like TCP retransmissions. The sender just keeps trying to send the message until it gets an acknowledgement that it was received.
So putting it all together, the provable security, those guarantees of consistency, everyone agrees on the state eventually, and liveliness, the chain keeps moving, these are mathematically proven if and only if you accept these two fundamental assumptions are true.
That's the core of it, yes.
Assumption 1, the number of malicious nodes is strictly less than 13 of the total. Assumption 2, the underlying network, while potentially slow, will eventually deliver messages reliably between the honest nodes.
That's the precise technical foundation as laid out in the source material we looked at. It's a conditional guarantee, absolutely dependent on those foundational assumptions holding true in the real-world deployment.
Okay, wow. We have truly done a deep dive then, haven't we? We've gone through all the layers of Scale's consensus mechanism, starting from the moment you submit a transaction, all the way through block proposal, consensus, finalization, and finally, storage.
Yeah, we've seen how those phases, like the block proposal and especially the DA broadcast, use that critical 23 signature requirement. It's really cleverly engineered to ensure proposals are, 1, widely available across the network, and 2, uniquely identified, preventing those easy double-spend type attacks.
And we explored how the block consensus phase, using algorithms inspired by that classic Byzantine generals problem, provides a way for all the honest nodes to agree on the single winning proposal for each block slot, even if some nodes are trying to cheat or fail.
And we've unpacked the foundation of Scale's provable security claims, those guarantees of eventual consistency and liveliness. And crucially, we understand now that these are mathematically proven, but under those specific critical assumptions, fewer than 13 malicious nodes and a network that guarantees eventual message delivery between the honest ones.
So what does this all mean for you listening?
Well, understanding these intricate layers, these phases, these thresholds, it isn't just about the tech jargon. It really gives you insight into the fundamental design choices, the engineering, and maybe even the trade-offs involved in building a blockchain system that's aiming for both high performance and strong mathematically backed security guarantees for dApps. It shows you the complex machinery working underneath. Right. And thinking about those foundational assumptions, especially the network one, brings us to a final thought, something maybe for you to consider further. Given that reliance on the network eventually delivering messages and that strict limit on the proportion of malicious nodes, it does raise an important question, doesn't it? How might real-world conditions, things like sustained network partitions or perhaps unexpected correlated failures of nodes that look like malicious behavior, even if they aren't intentionally so? How might deviations from those core assumptions impact the practical guarantees of consistency and liveliness in a live running scale chain environment? It's definitely something worth pondering as you continue your own explorations into decentralized systems.